In this section, we're going to be looking at equations where it's really important that you check your solutions, not just to make sure they're correct, but we're going to be solving equations where we could end up with extra solutions that don't work. So the first example we're going to look at is we're going to look at equations that have roots in them, like a square root or a cube root, and so on. So the goal here is to get rid of the root, because if there's a variable underneath it, you have to get the variable out from underneath the root to solve for that variable. If possible, you're going to isolate the root on one side of the equal sign. Sometimes it's not possible. And then once you do that, you're going to, if it's a square root, you're going to square both sides of the equation and then solve. And that way you would be getting rid of the square root. Now, when you square or cube or take it to the fourth power, an equation, what you're doing is you're making it bigger. And since you're making it bigger, it is possible that you could end up with some solutions that don't work, which is why we want to check our solutions. You could have extraneous or extra solutions that just don't work. In example 1a, we have the square root of 5x minus 1 plus 5 equal to x. So my goal is to get the square root by itself. The first thing I'm going to do is I'm going to subtract 5 from both sides. And then I'll have 5x minus 1 underneath the square root equal to x minus 5. Now that I have the square root by itself on one side of the equal sign, what I can do is I can square both sides. And now here on the right, it's not simply x squared minus 5 squared. You're squaring everything. It's the x minus 5 in parentheses squared. So you're going to have to multiply or FOIL that out. Now on the left-hand side, the square and the square root will cancel. And we have 5x minus 1, which was our goal. Our goal was to get rid of that square root. On the right-hand side, remember, this is x minus 5 times x minus 5. So you will have to multiply that out. And when you do, you should get x squared minus 10x plus 25. So now I see that I have a quadratic equation. I'm just going to bring everything over to the right-hand side where the x squared is. To get x squared, if I minus 5x, I get a minus 15x. Add 1, I get a plus 26. And that will be equal to 0. Let's see, this should factor as x minus 13, x minus 2. Is that right? Yes, I get x squared. Minus 13 minus 2 is my minus 15x. And then I get plus 26. So I have two possible solutions, x equal to 13 and x equal to 2. However, since I squared both sides of the equation and made it bigger, these solutions may not work. I need to check them. So off to the side, I'm going to check these solutions. And when you check, make sure that you put those solutions into the original equation you were given, because you could have had some math errors along the way. That will give me the square root of, if I put in 13, 5 times 13 minus 1 underneath the square root plus 5. So the question is that equal to 13? I don't know. 5 times 13, that should be 65. Minus 1 is 64. So I'm going to have the square root of 64 plus 5. That's 8 plus 5. Is that equal to 13? And the answer is yes. So this checks out, and x equal to 13 is a solution. So let's look at x equal to 2. If I put in 2, I get 5 times 2 minus 1 underneath the square root, plus 5, and then is that equal to 2? So 10 minus 1, that's the square root of 9, plus 5, and I can see that this is not going to work. This ends up to be 3 plus 5. That's not equal to 2. So I can't use 2. And that's the point of this section, is that whenever you square or cube or fourth power both sides of an equation, you're making it bigger. You could end up with solutions that don't work, so check your solutions. In this next example, in part B, we have two square roots. So you don't want to square both sides the way we see it. I'll show you what it will look like. If you square both sides, on the left-hand side, you would have to FOIL that out. It's the square root of x minus 2 plus square root of 3x minus 8 times square root of x minus 2 plus square root of 3x minus 8. You do not want to do that. It's not wrong. It'll just be a huge mess. So take and subtract one of those square roots and move it on to the right-hand side. And it doesn't matter which one you choose. So if I kept the square root of x minus 2 on the left, and I subtracted the square root of 3x minus 8, then I have isolated the square roots on either side. Now I do have a negative in front of the square root on the right-hand side, but that's fine. When I square both sides, on the left-hand side, the square root and the square will cancel, and I simply have x minus 2. On the, did I say left or right? Left, x minus 2. On the right-hand side, since I'm squaring it, that negative in front of the square root will turn positive. So in this case, this will just be 3x minus 8. I've gotten rid of my square roots. I can go ahead and solve for x. I think I'm going to minus x from both sides and bring everything over to the right, and then add 8. So I'll get 6 equal to 2x, and x is equal to 3 as my possible solution. And when I check that, I'm checking it in my original equation. This is going to be the square root of 3 minus 2 would be 1. Plus the square root of 9 minus 8 would be 1. Is that equal to 0? No, that's 2, which is not equal to 0. That was my only possible solution, and it didn't work. So there's actually no solution to this equation. So I could write no solution. Or remember, we have that empty set symbol. And this 3 did not work. And I kind of knew it wouldn't when I looked at the original equation, because these are square roots. They can be 0 or they can be positive, but they'll never be negative. So when you add them together, the only way that the equation can be true is if both square roots are 0. And in this case, that would be impossible. Now let's look at some examples where we have higher roots. In part C, we have a cube root, the cube root of 9 minus x plus 2 equal to 0. So the process is still going to be the same. We're still going to get the root by itself. I would subtract 2 from both sides to get the cube root of 9 minus x equal to negative 2. And then at this point, to get rid of the cube root, I'm going to cube both sides. So remember, to get rid of the root, the exponent has to match the root. That will give me 9 minus x on the left and negative 8 on the right. If I subtract 9 from both sides, I get negative x is equal to negative 17. So x is equal to 17 would be a possible solution that I will check. And when I check and put in 17, I have the cube root of 9 minus 17. So that's going to give me the cube root of negative 8. Plus 2, is that equal to 0? Cube root of negative 8 is going to be negative 2. So yes, it checks out. And x equal to 17 is a solution. Now, what if we took that same equation, but instead of using a cube root, I use a fourth root? So if we have the fourth root of 9 minus x, again, isolate the root by subtracting 2 from both sides to get the fourth root of 9 minus x equal to negative 2. And already I could see that there should be no solution for this because an even root can never be negative. But I'll go through the process anyway. At this point, I would take it to the fourth power on both sides to get 9 minus x equal to a positive 16. We'll get negative x is going to be equal to minusing 9 from both sides would give me a positive 7. And x is equal to negative 7 would be a possible solution. When we check that, I have the fourth root of 9 minus a negative 7 plus 2. Is that equal to 0? This would be the fourth root of positive 16. And that would be a positive 2. So no, these don't check out. And in this particular case, I have no solution. So the solution set is the empty set. Now, if you have two cube roots, or even two fourth roots and so on, in one equation, the strategy is going to be the same as we had with our prior example. You would isolate one root on one side, and then take the other root, subtract it, get it on the other side of the equal sign. I have the cube root of x squared minus 2x is equal to a negative cube root of 5 minus 4x. So now we have to cube both sides. And here we do have to be careful on the right-hand side. Left-hand side, cube root cancels. And I have x squared minus 2x. But that negative in front of the cube root, it's going to stay because this is to the third power. A negative 1 to the third power is still negative 1. So just be careful here that you have the negative and then in parentheses 5 minus the 4x, because you are going to have to distribute that negative. We get x squared minus 2x is equal to negative 5 plus 4x. And now I see I have a quadratic equation. I am going to get everything on the left-hand side, set it equal to 0. To get x squared minus 4x from both sides will give me a minus 6x, and then add the 5. So it looks like this should factor into a minus 5 minus 1. So x minus 5, x minus 1. Possible solutions would be 5 and 1. Now let's go ahead and check those. If I put in 5, I will have the cube root of 5 squared, so that would be 25 minus 10 plus the cube root of 5 minus 20. Is that equal to 0? And this would be the cube root of 15 minus, or plus, sorry, the cube root of negative 15. And yes, this is going to be equal to 0. Because this is a cube root, and look at the negative 15, that's negative 1 times positive 15, you can actually pull that negative out. So it becomes a minus cube root of positive 15, which will be 0. So that checks out. You can always just put in the calculator as well, and you'll get 0. Now let's go ahead and put in positive 1. So we'll have the cube root of, this would be 1 minus 2 would be a negative 1, plus the cube root of 5 minus 4 would be a positive 1. And we have the same situation. This becomes negative 1 plus 1. Checks out. In this particular case, both of these solutions work. And I don't know if you notice this, if the root is odd, like a cube root, typically the solutions will work out, but if you have even roots, square root, fourth root, and so on, oftentimes the solutions do not work out. And now let's look at some other equations. And although these are not equations involving roots, they are equations involving negative integer exponents and then rational exponents. So we do have to be careful with these as well to make sure that our solutions do check out. In the case of negative integer exponents, recall that if I were to make these exponents positive, so this is example 2a, I would write this as 2 over x squared plus 5 over x, and then equal to a negative 3. So that x is now in the denominator of a fraction. If I get, in this case, 0 as a possible solution, I can't use it because it will give me undefined denominators. So this is a case where you do have to check your solutions just to make sure that, not that they work necessarily, just that they don't give you something that's undefined. At this point, I could simply multiply both sides by the LCD x squared and clear the fractions, and typically that's what I would do. But I would like to go back to the original equation and show you another method that you can use if you want to get rid of negative integer exponents. So I'm going to rewrite this 2x to the negative 2 plus 5x to the negative 1. And I'm going to add 3 to both sides, write it as plus 3 equal to 0, because it kind of looks like a quadratic equation. So we could also do a substitution on x to the negative 1. And we used that technique before as well. However, I'm going to do something else. What if we were to look at the smallest exponent? In this case, it would be a negative 2. And what if I were to multiply both sides of the equation by x to the, instead of negative 2, do a positive 2? Distributing, I would have 2x to the negative 2 times x to the positive 2. Now, normally I wouldn't even show this step because I already know that this is going to be x to the 0, which would give me 1. Plus 5x to the negative 1, x to the positive 2, plus 3, x to the positive 2, and then equal to 0. Same base means we add the exponents, so x to the negative 2, x to the positive 2 becomes x to the 0, which is simply 1. And this becomes 2. Plus 5 times x to the negative 1, x to the positive 2 becomes x to the 1. So 5x plus 3x squared equal to 0. So again, you could have worked with the fraction, multiply both sides by x squared, which is essentially what I did to get rid of the fractions and then kind of go from there. You could do a substitution on the x minus 1. Or you could multiply both sides by the positive value of the smallest exponent and then get positive exponents. Now this is quadratic. This is 3x squared plus 5x. I'm sorry, it's hard for me to factor it if the x squared's not in the front, so I always rearrange. That's just my thing, you don't have to. So let's see if this does factor. So it should be a 3x and an x. The 2 would probably go with the 3x. So 3x plus 2x plus 1. Let me check. 3x squared, I have a plus 3x plus 2x would give me the plus 5x. Yeah, and then I get the plus 2. So my possible solutions are going to be x equal to minus the 2 divided by 3, so negative 2/3, or x equal to a negative 1. And when I check those solutions, maybe I'll just plug it in a calculator to check. This is going to be tedious. It's going to be 2 times negative 2/3 to the negative 2 plus 5 times negative 2/3 to the negative 1. And the question is that equal to negative 3? So when I put this in a calculator, I have 4.5 plus a negative, so minus 7.5. And it checks out. So the negative 2/3 does work. The other possibility was a negative 1. So 2 times negative 1 to the negative 2 plus 5 times negative 1 to the negative 1. Is that equal to negative 3? So negative 1 to the negative 2 turns into a positive 2. And then here, this would be a minus 5. Again, you could just put this in a calculator, and that checks out. That'll be negative 3 equal to negative 3. So in this case, both of the solutions work out, which is awesome. Let's look at the other case where you would have to check your solution, and that's when you have rational exponents, because it could end up that you have an even root. So let me translate this equation. This is x plus 3, and instead of x to the 1/2, I'm going to write it as the square root of x. So notice here that I have the square root of x. If I end up with a negative x value as a possible solution, it's not going to work because I can't have a negative underneath the square root. And that's why we have to check solutions when you have rational exponents. In this particular case, I could perhaps isolate the square root and do what we did before. But I think I'm going to go back to the original equation. Notice that this is x to the 1 plus 3x to the 1/2 minus 4 equal to 0. And I know if I take 2 times the 1/2, I get the 1. This is a good candidate for a substitution. I would like to review substitution. So again, we could have done the isolate the square root of x, square both sides. But instead, I'm going to do a substitution just for review. I'm going to let u be x to the 1/2. Because I know when I square u, I'm going to get x to the 1/2 squared, which is simply my x to the 1. So now this is going to be u squared plus 3u minus 4 equal to 0. And that's easier for me to see the factoring, which should be a plus 4 minus 1. Again, you didn't have to do it this way. It's just a nice time to review substitution. And to remind you that when you get down as far as you can go, in this case, I have u equal to negative 4, u equal to 1. I have to substitute the x back. Remember, we're trying to find x values and make the equation true, not in this case u values. And remember, our u was x to the 1/2 equal to negative 4, and x to the 1/2 equal to 1. Right away, I could see that x to the 1/2 equals to negative 4 won't work because that's the square root of x. It can never be negative, but again, let's say that I'm on autopilot. One way to get rid of the 1/2 is to square both sides. So this is x equal to 16. And on the other equation, if I square both sides, I have x equal to 1. When we check these solutions, if I put in 16, I will have 16 plus 3 times 16 to the 1/2 power, and minus 4. Sorry, I had to check my equation, equal to 0. Is that true? And the answer is no. This is going to be 16 plus 16 to the 1/2 is 4 plus 12. That's not equal to 0. So I can already tell that's not going to work, and I knew it wouldn't. If we put in 1, we'll have 16 plus 3 times 1 to the 1/2, which is simply 1, minus 4. Oh, 16. Why did I put 16? Autopilot. It's going to be 1. Plus 3 times 1 to the 1/2 minus 4. Is that equal to 0? Yes, because you get 1 plus 3 minus 4. Okay, so that was the caution there. If you have the negative exponents or if you have fraction exponents, don't forget to check your solutions. Oops. And the 1 does work. The 16 does not. And that's it for this section.